Yes,
start
sir.
sharing. Yeah, I'll start sharing my screen.
Sure.
Yeah, I hope the screen is visible.
Yes, it's visible now.
Yeah.
So you can do it full.
Yeah, I'll do that.
Yeah, that's
Okay,
fine.
so good afternoon, everybody, and I take this opportunity to thank. Uh, put on my camera.
Your voice has gone.
Some voice is not there.
No, I just turned on my camera, and
Oh,
I hope
okay.
everything is right now.
Yeah, it's right now.
Yeah, and the screen is also visible. Yeah. So I take this opportunity to thank IEEE chapter, Jaipur, IEEE Jaipur chapter for inviting me to deliver this talk on antennas for millimeter wave 5G applications. This work that I'll be presenting today is part of the PhD work of my PhD student, Dr. Zamir Wani. He recently graduated with a PhD degree here. So that's the reason I've listed him as well as one of the you know, authors here, though I will be presenting, but he also has contributed to make this work as well as to the slides. So a brief outline of my today's talk. I will briefly introduce the millimeter wave communication. Why is it important? What are the challenges? And what are the opportunities? So when we say what are the challenges also mean opportunities. So what are the different opportunities that one has when we deal with millimeter wave applications, especially antenna applications? Then I'll present a few of the antennas that we have worked here at IIT Delhi. So first one is antenna with a wide stand coverage for millimeter wave application. So this millimeter wave applications, the entire work is done at 28 gigahertz. So although I'm saying millimeter wave application, the work is specifically at 28 gigahertz. Then millimeter wave MIMO antennas for 5G applications. Then we discuss design of a dual beam antenna using single epsilon high anisotropic media, and then finally we'll discuss millimeter wave lens antennas. And as we know, lenses help to increase the gain of the antennas. So at millimeter waves, we'll look at some examples of lens antennas using various techniques. The lenses are created using various techniques. So this is the outline of the talk, and finally, of course, I will conclude briefly, and then I will take question answers. But please feel free to ask questions in between as well. So why this millimeter wave is important as a good means of communication. So as we all know, existing technologies 3G and 4G and wireless LAN, they are lacking the necessary data rates required for new applications. For example, home entertainment, virtual reality applications, home TV broadcasting and streaming, and so on. So all these applications require a lot of very high data rates, and the existing 3G and 4G technologies, they do not support very high data rates. And as the applications evolve, like we will move from 4G to 5G, 5G to 6G, and so on. So that's how it will go on, depending on how the applications evolve, how the need for higher data rates evolves. Millimeter wave spectrum promises higher data rate of the order of multi-gigabits per second speeds. Because at millimeter waves, even if you have 1% bandwidth, let's say at 28 gigahertz, if you have 1% bandwidth, that's a huge bandwidth. 1% of 28 gigahertz will be a huge bandwidth. At 10%, again, will be a huge bandwidth. So at lower frequencies, however, 1%, 10%, the total absolute bandwidth is much smaller. Therefore, millimeter wave is picking up pace for communication applications where higher data rates are required. So some primer on 28 gigahertz band. So the ITU in WRC 15 and US FCC have identified 28 gigahertz, 39 gigahertz, 64 gigahertz, and 71 gigahertz as the millimeter wave bands. And more recently,
Excuse me, sir.
yes.
Sir, little bit voice is not clear. Sometimes it's coming and sometimes it's not coming.
My network is good. I'm on Institute land, so network speed should not be a problem.
Yeah, now it's coming.
Is it okay now?
Yeah, sir, it's okay now.
Yeah, it's okay.
So more recently, there have been additional frequency bands which are identified for next generation 5G deployment, which are 24.5 to 27.5 gigahertz, 37 to 43.5, 45.5 to 47, and so on. So different countries actually specify different bands for communications. So 28 gigahertz band allocation, bands above 24 gigahertz for possible mobile use. So 27.5 to 31 gigahertz, and then you have 37 gigahertz to 42.5 gigahertz. So here you can see this blue uh, dark blue regions. They are bands proposed for mobile use, whereas this one, the other one, they are for bands raised in NOI. So different bands are available at millimeter wave frequencies. For 28 gigahertz specific bands, let us look at some of the channel characteristics. Say path loss for various frequencies. So the table on your left shows frequency, and in the second column we have path loss at a distance of 10 meters. And so we have at 2.4 gigahertz, the path loss is roughly 60 dB. If you go higher up in frequency, the path loss increases. At 28 gigahertz, we have 81 dB path loss at 10 meters from the transmitter. Blockage, tinted glass. With tinted glass, the 28 gigahertz band blockage is about 40 dB. With bricks, it is about 28.3 dBs. And atmospheric absorption. So average atmospheric attenuation is 0.06 dB per kilometer, and so which translates to 0.012 dB for 200 meters. So these are the channel characteristics. So the question to be asked is whether the free space path loss is high, right? This 81 dB free space path loss, whether this is very high. It is not very high. Right? Like if we compare it with 2.4 gigahertz, it is 60 dB. This is 81 dB. Right? Atmospheric attenuation too high, not really. Air attenuation too high, not really. So for 200 meters, 1.2 dB attenuation is observed at 28 gigahertz. So this is taken from a paper by Dr. Rapo. So what we get is at 200 meters, we get an attenuation of about 1.2 dB. Okay. Now this requires still the distance, communication distance here is written as 200 meters. So if you want to really increase the communication distance, you really require very high gain antennas with narrow beam widths. So this is another graph showing channel measurements. So we have on y-axis, this is the maximum coverage distance, and on x-axis we have combined transmitter receiver antenna gain. And this is the parameter n that is used here. Is its value is true for free space. Again, this is from a paper by T.S. Rappaport. So this is 213 paper. So this parameter n that is used, different curves that you see here, is n equal to 2 is for free space, and if you have obstructive environments, n is equal to 5. So more the obstructions, the value of n will keep on increasing. So what we see here is, say for example, the maximum coverage distance, if it is to be around 350 meters, right, the gain, the combined gain of the transmitting and receiving antenna under this objective condition n equal to 4 is about 30 dBi. Okay? So naturally, when you want to increase the coverage distance, the gain will proportionately go higher and higher. Now, what we see across, if I move across this line here, so what I see is for they're not really overlapping. Say, for example, in this case, for 600-meter distance, the free space n equal to 3, which is very close to free space, will require a gain of about close to 18 dBi, whereas with the same gain, the coverage distance with obstructions and more greater values of n equal to 4, 5, or 5.76, the coverage distance is much smaller. So if you have less obstructions with the given gain, you can achieve more coverage. So which is generally true for any other communication as well. But this is the scenario for the 28 gigahertz band. Another advantage of millimeter waves is millimeter wave devices will accommodate dozens of antennas, because antennas, as you increase the frequency, the wavelength decreases. As a result, the antenna decreases, and therefore this will enable MIMO. Right? So you can accommodate dozens of antennas due to small wavelengths to enable MIMO operation as well. So this is another advantage of using 28 gigahertz band. So MIMO, two scenarios. One is beamforming with digital architecture. Other is for antenna gain. You can use beamforming, and other one is for spatial multiplexing or for spectral efficiency increase. You can use this MIMO configuration as shown here. Multiple transmitters, multiple receivers. So the antenna requirements at the millimeter wave frequencies, and more specifically at 28 gigahertz band. So first, if the issue is of propagation loss, we can overcome that by using highly directional antennas. But when we use highly directional antennas, what happens is the coverage is limited. Highly directional antennas would mean the beam width is very narrow. As a result, the coverage is less. So to improve this coverage, you can use wide scan antennas for non-line of sight applications. So if you are scanning antennas with wide scan capabilities, then this coverage problem can be solved. Then there is shadowing. So shadowing can be overcome by using dual beam or multi-beam antennas, and in addition, you can also use MIMO configuration. Now, this dual beam or multi-beam antennas, they will result in system losses and complexity. Therefore, to overcome this system losses and complexity, lens antennas with antenna arrays can be used for massive MIMO applications. So these are some of the issues and solutions. So based on this, so some of the literature that reports some of these solutions is shown here. So gain enhancement technique, first is array. But in arrays, as we all know, the feed losses are very high at millimeter wave frequencies. So the way it is shown here, these are the antennas. This orange colors are the antennas, whereas this brown color is your feed network. So the feeding network has high losses because there are a lot of lines used. Obviously, the losses will be very high. Then we have epsilon negative or near zero medias, epsilon near zero or permeability near zero medias. So these are also used for high gain applications. However, these ENZ or MNZ medias, they are narrow band and their impedance matched only for in most cases, their impedance matched only for normal incidence. Right? What happens is when the incoming wave is obliquely incident, and the impedance matching is not very good. Therefore, these have limited applications again. However, we will be doing, I'll be demonstrating one application using this type of media, but with a different perspective. Then another way of gain enhancement is using resonant cavities. In resonant cavities, again, as it is resonant cavity, they are highly sensitive to the cavity dimensions, height, and they're usually narrow band because they are resonant cavities. They are narrow band characteristics. Then millimeter wave MIMO antennas. So this what is shown here is a 3-port dielectric lens antenna. So you can see there are 3 ports here, R, C, and L. So right, center, and left. And then there is a dielectric lens. So this is a foam formed to keep the GS lens aligned with the antenna, and this is the lens. However, these type of antennas are bulky for handheld applications. Then dielectric resonator antennas for MIMO applications. These again, the gain that is reported is limited, only 8 dBi gain for each port. And one would expect that one has more gain for millimeter wave applications. Then other antennas that are reported are dual band antennas. So these were the gain enhancement techniques. Then we have dual band and dual beam antennas. So you can see here, this is your feed structure. And then they have used periodic structures on either side. This is a dipole antenna with periodic structure on either side. So this results in a dual beam characteristics. Then we have cavity backed antennas, which again give dual beam. So you can see that there is a almost a null along 0 degrees here, and then 2 beams. Then lens antennas, planar lens for multi-beam applications. So this can also be used. So using a lens on top of an antenna, you can get multiple beams. So this reduces the number of RF chains that are required. Phase compensation is done using, so in this particular application, there are 4 substrates that are used, 4-layer planar lens. And the unit cell of 4.5 mm is used. But this generally, a lot of times it results in phase errors. If you use multiple layers of periodic structures as a lens, it results in phase errors. Plus, it increases the overall size. So the gain that the increased gain that we obtain is not in proportion to the size of the overall radiating system. And as is shown here, the aperture efficiency is only 16% in this case, which is very low. Although the gain may be high, but the aperture efficiency is very low. That's one of the disadvantages. So looking at these, limited literature survey that I have presented, of course we have done a quite exhaustive literature survey, but only limited cases were presented. So the opportunities that one has in this field is one can design high gain antennas with wide scan radiation characteristics to avoid any signal blockage due to objects. So it is high gain as well as wide scan characteristic. Then we have design of compact antennas for MIMO capabilities. Then dual band generation techniques with wide dual band bandwidth and realization flexibility. The new techniques for antenna gain enhancement or wide bandwidth. So gain enhancement is usually done with a limited narrow band application. However, the opportunity is to increase the gain over a wide band of frequencies. And last but not the least, design of thin planar metasurface lens with antenna array for again multi-beam MIMO applications. So you have planar lens, metasurface lens, you have multi-beam, and we have MIMO configuration. So all put together, one can design antennas of that type. So first is a wide scan coverage for millimeter wave application. So the antenna, we start with a dipole antenna, very simple dipole antenna. So this is the top view, and the back view also will be similar with opposite arm. So on top view we have arm like this. On the back side, the arm will be opposite direction. So simple antenna with very good S11 characteristic. S11 typically represents the impedance matching. So the lesser it is, the better impedance match we have. So, and this is the gain. So typical dipole antenna that is presented here. Then we load that dipole antenna with metamaterial loading. So this is the unit cell of the metamaterial. It was characterized for S parameters. So what we see here is it has a dip in transmission. Right? Red curve indicates S21, that is transmission, and impedance matching is indicated by the red curve, which is S11. Sorry, The black curve indicates the transmission S21 and red indicates the impedance matching or S11. So what we see here is at one frequency, right, one has or a frequency band if I take, right, you have no transmission through this unit cell, and the unit cell is placed in this direction because we will be placing this unit cell right in plane with the dipole antenna. And then in this graph on your bottom right, this is your epsilon effective, mu effective, and refractive index effective. So the black curve is epsilon effective. So what we see here is beyond this frequency, you get negative epsilon. Likewise, the mu is very close to zero, and refractive index is also very close to zero, except at this frequency where your transmission was very low, almost no transmission at all. So this is the loaded picture dipole antenna with the periodic structure. And this is a simple periodic structure, nothing very great about this structure. So what is done is, so we can see here the dark region, the dark inverted L-shaped line is the top layer, whereas this slightly lighter shade is on the back side. And then you have ground plane on the back side. This is limited ground plane. And this is the periodic structure, arrangement of the periodic structure. This is fabricated antenna with southwest connector and launch connector up to 50 gigahertz. So what we see here is the impedance matching is good over the entire band, 26 to 30 gigahertz, measured as well as simulated results match. So this is just the preliminary study. We'll discuss more interesting examples based on this. And then what we see here is the phase of EX. Right, what is shown here, the phase of EX at Y equal to 6 mm and WT equal to 0, radiated from the dipole antenna with and without. So what happens in this case is the gain improvement is more because of the phase equalization. Right? So the waves that are coming out of this dipole, and they are passing through this periodic structure, and when they come out, we are measuring the phase of the waves that are coming out of from the x-axis. What we see here is without the metal layer, without ML, this red curve is what is seen. So what we see is the phase is varying across the x-axis. So this is your center to the left, to the right. Whereas if we use this metal layer, what we see, the phase has more or less, is normalized. Right? You get roughly constant phase for x component of electric field across the x-axis, across this axis. So as a result, what happens is, because of this phase equalization, right, we get gain enhancement from this dipole antenna. So the phase equalization is also seen here. This is without and this is with. So what we see here is the curve, the graph on your left bottom shows gain versus frequency. So black is simulated without the metal layer, just the dipole antenna. So the gain is about 6 dB high. And we have red one is simulated with metal layer, and blue is measured with metal layer. So what we see is there is sufficient gain increase with the metal layer, and this gain increase is mainly because of the phase equalization that was shown here. Okay, so the phase, we get phase equalization, as a result we get a good amount of increase in the gain. So decrease in 3 dB beam width to 41 degrees from 64.5. So the black curve is for without metal layer, and blue curve is for with metal layer, simulated and measured. So the beam width has decreased. As a result, the peak gain, simulated peak gain, touches 11 dB. So that's quite a good gain from a single dipole antenna with the metal layer structure. Now the same structure was modified to tilt the beam. Okay, so as we observe here in this figure here, so what happens is most of the field is concentrated in this periodic structure. So what was done was to tilt the beam. So this is along a particular direction. So this is at 90 degrees. So to tilt the beam, what was done was this metal layer was shifted along x-axis. So as a result, what happens? So this is the fabricated one. Again, the S11 measured and simulated, they match roughly well over a band of frequencies, 25 gigahertz to 31 gigahertz. Now this is beam tilting technique. So what is shown here is this is your antenna and this is your metal layer surface. So in this case, there is no metal layer, gray region, there is no metal layer, whereas in this green region, there is metal layer. So we have N substrate and we have N for the metamaterial. So this LM is the length of the metamaterial. Right. So by observing the phases, by observing the path lengths and phases, one can deduce as to at what angle will the beam tilt. So what is seen here is for particular values for x equal to plus 6.32. So x equal to plus 6.32 is this. So this is the center, dipole center. From here we are moving the center of the periodic structure here by 6.32 mm. So it's this 6.32 mm. So if for x equal to 6.32 mm, Lm, that is length of the metal layer, Wm is the width. This is your N substrate that is used, and Nm. So this was calculated, Nm. So what we see is the tilt angle that we obtain is about 66 degrees. So by varying these parameters, we can change the tilt angle. And so this is what is shown in the graph, the radiation pattern. So this is dipole antenna with offset metamaterial loading. So what we see is the multiple curves here. So this is with metamaterial and for various offsets, plus 2.32, minus 6.32, plus 6.32, and this one, the gray one, dark gray is the major one. So this dark gray and blue are to be matched. So these are to be seen. So what we see here is, for example, the red curve, minus 6.32, and you get this beam tilt. So the beam is shifted. Likewise, for if it is less, x is 2.32, the beam shifts to a smaller angle, and so on. And so this is all with metal layers. So without metal layers, you will have the beam tilted. Without metal layers, the beam was, well, if the metal layer was at the center, the beam was at 90 degrees. Now it has shifted. And this is dipole antenna with metamaterial loading. So what was analyzed was Ex was analyzed for various distances, x equal to 2.32 and x equal to 6.2. So these are random numbers, 2.32, 6.32. They don't have any significance. One could have done it at x equal to 4 and x equal to 8 as well. So there is nothing much to read about it. And phase. So what we see is phase becomes more or less linear, right, for the two cases. The linear curve is shown here with dotted lines. So as a result, one would get more gain enhancement. So using these two techniques, what is shown here is a quasi-Yagi antenna with metamaterial. What we see here is there are three Yagi antennas. Okay. So center, left, and right, and then we have this metamaterial loading. So what happens here is for this Yagi antenna on the left, okay, the metamaterial is on the right. Okay, so it will radiate in a particular direction. For the center one, it will radiate in the forward direction. Whereas for the one on the right, it will radiate in the other direction. So you should get three beams when all the three are activated, or all the three are fed at this point, A1, A2, and A3. So there was a parameter study done. So what was seen was the angle here, this angle alpha at which this is tilted. Where it is 15 degree, you get sufficiently good parameters. gain is reasonable 10.9, side lobe level is at -10, beam tilt is 29 degrees, and front to back ratio is 19.8. So reasonably good parameters are obtained when uh, your angle alpha is 15 degrees. So uh, what is shown here is S22, so basically impedance matching for various gap parameters. So this is important. So what we see here is there were three antennas. So when they are excited separately, right, so they tilt the beam in three directions. So you can see this is going along your right, this is going towards your center, and this is going towards your left. So in the same antenna, we get three different beams. So this is shown as 2D plots, gain versus the angle phi. So for the center case, you get 90 degrees, and then here we get at 60 degrees, and here we get at 120 degrees. So 30 degrees plus minus 30 degrees from the main beam is what we obtain. So one can analyze this with the electric field with and without metal layers as well. So what we see is with metal layers, the field is concentrated. So without metal layers as well, you can see the field is pointing towards the right for this case. With metal layer also it is pointing, but the phase, there is a phase equalization that is happening. As a result, you will get gain enhancement. So return loss and isolation between elements, because these three are placed very close to each other. So isolation was generally good. So it was, except for this X32 case, which was about 15 dBi, 16 dB, sorry, 16 dB. Rest of it is better than 20 dB. So your isolation is also good. And gain enhancement. Now what we see here is gain has been, the gain of first antenna is 10.85, gain of the second antenna is 11.3, and third antenna, which is similar to first antenna, it will again be 10.85. So these two curves are without metal layers, whereas these are with metal layers. So for all the three beams that we get, you get very good gains. So experimentally it was shown. So again you get three different beams depending on which port is excited. So this is at 27 gigahertz, this is at 28 gigahertz, and 29. So in the entire band, you get good three beams. Then other parameters, because it was used in MIMO configuration, three very close antennas. So other parameters were studied. Envelope correlation coefficient was studied, so it was good for all the three antennas. Total efficiency was studied. So total efficiency is also above 75% for all the three cases. Diversity performance was also studied. So it was seen that the diversity is also good. So, and it is plotted here, diversity gain is plotted here, whereas the multiplex efficiency is plotted on the right axis. So you sufficiently get good diversity gain as well as multiplex efficiency. Then it was compared with existing, and it was seen that this proposed work is better than in many aspects with the reported ones. So some of the parameters like this isolation, for reported works it is 20 dB, 30 dB. Here it was 16 dB only. However, this was because the ports are very close. So if I take the ports apart from each other, and the antennas being there the same, but the ports are taken apart, so this can be further improved. The next is millimeter wave MIMO antennas for 5G application. So again, taking clue from this particular geometry here. So this was expanded further. So what is seen here is, so this was the original case, and so this is put in a MIMO configuration. So same two antennas. So this is port for the left antenna, this is port for the right antenna, and then to increase the isolation, there is a small stub introduced. So this small stub is a standard technique in MIMO configurations for increasing isolation. stubs, or you many times if the structure demands, you create via holes to increase isolation. So in this case, a small stub was done, and then it was realized that you don't really require all of this periodic structure. Only part of it is required. So this is a trimmed uh, periodic structure. So you can see that some of the cells are removed. In this case, without the stub, this is case one. So what we see here is if port 1 is excited, there is coupling to port 2. When you clean this, the coupling automatically reduces. So nothing goes here. In this region, you see green. So this is the scale. Red one means high field, high current, and blue is low current. Right? So you see that there is no current going to the port here. The beams, because there are two antennas used, and the way they are configured, so this antenna sees this in a at some angle, and this antenna sees this at some angle, at other angle. So what we see is if you get two beams, so that is what is observed. One is pointing towards right, another is pointing towards left. The two beams are obtained. Then same thing. So same thing was slightly modified and put as a four-port configuration. So you have P1, P2, P3, and P4, and then the periodic structures, three periodic structures. So they were fed. This is fabricated structure. So they were fed, and isolation and other things were measured. This is the antenna pattern measurement setup, where the antenna is placed on a turntable, and King band horn antenna is used as the transmitter. So I go to the important parameters here. So we see the gain. So what we see here is for port 1, the 30, this is 30 gigahertz and 29 gigahertz. So what we see is gain is sufficiently high at both the frequencies. So let's see the gain at 30 gigahertz, P1, and at 29 gigahertz, P2. So these are the two curves. So this is at 30 gigahertz, and this is at, sorry, 1. So this is basically the P2 at 29 and 30, and this is P1 at 29 and 30. So we see that there's sufficiently high gains, plus the beams are in different directions. So this will give us a better picture. So this is first, the direction is here. Second, the direction is somewhere here. Third, it is along this side, and fourth is along that side. So you get 4 different beams from this configuration. And isolation, I didn't harp on the isolation parameter. Isolation is better than minus 21 dB for the entire band, 26 to 31 gigahertz, so which is good. And when the isolation is better than 20 dB, it is considered to be a good design. So diversity performance, this is envelope correlation coefficient, and the gain, again satisfying the general specifications. Then you have diversity gain as well as this parameter, total efficiency and multiplex efficiency. So these are also satisfactory. So for in the first case we had 3 elements here, and then this was modified to get the 4 element. Again, the parameters are satisfactory, and it is again comparable to or better than the reported ones. Then we have under configuration dual beam MIMO antenna. So what is done is the Yagi structure that was shown earlier, right? It is now split as like this, right? So we have one port, and then it is split into 2 antennas. Likewise, the next port is split into 2 antennas, and these are the directors that we have. So this is dual beam. So you'll get one beam for this case and the second beam for this case. So this is a simple idea, not very complicated or not very long. However, the beams that we get, so what we see here, this is voltage per meter. If we get 2 beams. This is the fabricated one. So you are S parameters as well as isolation. So these are isolation parameters, S21, measured simulated. It is better than minus 25 dB for both the ports. And then the beams. So each beam is separate. So we'll get two beams from each case. So 60 degrees, 120 degrees, 150 degrees, and 210 degrees. So each port, when fed, will give into, we'll get two beams. Dual beam here, dual beam here. Again, diversity performance and other parameters were studied. So they also reasonably match the specifications that are given. Next is a design. So dual beam antenna was given here as well. This was, as I said, this was a simple technique to do dual beam antenna. So what was all that was done was we split this port, that incoming port, into two halves, and then each works as a separate act. So this will give you one beam, this will give you second beam. So next is this is interesting, design of a dual beam antenna using single epsilon high anisotropic medium. So so this is under three headings: theory and mechanism of single epsilon high anisotropic medium. Then we have dual beam technique for realization of this, and then prototyping experiment. So there is some theory that is that was developed. So of course, based on the literature of how does the single epsilon high anisotropic media works. So what is interesting in this is usually when you have dielectrics, so you get fixed values. So for example, if I take a dielectric sheet, it has a fixed value of permittivity. But if I want a dielectric sheet of, let's say, some random permittivity, it is generally not possible to get in the market. So what is done here is using this periodic media and stacking of these various layers. And so we have a periodic media, periodic structure on one layer. So if I call that as a meta surface, if I club these meta surfaces together, one can realize the parameter, the electromagnetic parameters epsilon as well as mu to any desired value. So that is what is the crux of the matter here. So we combine the layers. So these are some of the simulation ones using FTTD simulations. So what is interesting here is, yeah. So this is basically dipole antenna with single epsilon high anisotropic medium. Again, here in this case, you get two beams. Now, what is seen here is I'm assigning the values to the dielectric medium and then getting two beams. And in the simulation, I'm assigning the value of permittivities to the material, and then getting two beams. Now, practically, what is done is practically you realize that value of epsilon and mu by stacking multiple layers of metasurface. So for example, so this is the realization of single high epsilon medium. So all dielectric realization. So first is you use only dielectrics, and then obtain the value. So in this case, what is seen is your epsilon along x-axis is 7.9 and epsilon along y-axis is 1.9. Now this is something that one won't get in the naturally occurring materials. So these are designed so that you get any value here. So this is realized by using epsilon, two different epsilons. One is epsilon 1 equal to 40, this blue color, blue region that you see here, and second is air, epsilon 2 equal to 1. So by combining these two, as per Maxwell-Garnett theory, one can, and then this is filling fraction, how many layers are there. So one can get two different values for epsilon along x-axis and along y-axis. So this again shows this versus frequency. So red curve is epsilon x, epsilon along x-axis, and blue curve is epsilon along y-axis. So these are then used in a different fashion. So the earlier examples where the metasurface was placed in plane with the antenna. Here, the metasurface is not in plane; it is in a perpendicular plane. Right? So this is how it is shown, and this is your antenna. So this is basically SIW antenna, so integrated waveguide dipole antenna, and then these layers, these 7 or 8 layers, 8 slabs are used of a particular dielectric substance with air gaps in between, right, on the two sides. So what we see here is we get two different beams. We get two different beams. So this is at 25 gigahertz and this is at 29 gigahertz. Okay. Now this can also be realized using different. So instead of using an all dielectric, one can use a unit cell like this and then repeating this in XY plane, right, or different dielectric layers. So in this case, what is seen is your EX along epsilon along x-axis is 8.97 and that along y-axis is 1.43. So along different directions, you have different epsilons. So these are used. So other dimensions are shown here. This is 5.7 mm. This is 4.8 mm. So we are here. So you probably won't be. This is SIW dipole antenna. It's only the dipole. So this is again there's good impedance matching in the 28 gigahertz band, and then you get. This is for different number of slabs. This is for different number of slabs. So what we see here is if there is no slab, you get only one beam. So this is the beam that one would get. If you use 8 slabs, 7 slabs, 5 slabs, 3 slabs, 1 slab, and so on, you get different characters. So for 8 slabs or for 7 slabs that is used here, you get two distinct beams. And there is good dip here, about minus 15 dB dip between these two beams. So some fancy things from CST. So this is power in dB and this is EFA. So we can see this power is going in this direction and not this direction. And then there is something along, there's some along this as well, weak power. So that can be seen from here. This is the small amount of power that is going. At 3 frequencies, 26, 28 and 29, we get dual beams using 7 layers of this ELC MTM slabs. So this is the experimental element. This is your SIW antenna and 7 slabs with air gap between them. And this is measured radiation patterns, 2 beams at all the frequencies. So as you go higher up in frequency, there are small disturbances which are expected because the unit cell is designed at a particular frequency. Therefore, if you go higher up in frequency or change the frequency from that frequency, your radiation pattern changes because the parameters change. Then the gain is reasonably good for 7 ELC slabs. So what we have is gain is about 6 dBi or so, simulated and measured. So this is 6 dBi and roughly constant across the band, 26 to 31 gigahertz. So this was compared and it was found that our technique was better in many terms than the reported ones. Then design flexibility, you can design various values of epsilon x and epsilon y. So another unit cell is shown here. So what is seen here is for various unit cells. So this is epsilon x, epsilon x, epsilon y, epsilon y. This is for 8 slabs and single unit cell. 8 slabs and single unit cell. So one can change the unit cell and change whatever parameters you want, right? Or you can obtain the required parameters for the permittivity along x-axis and y-axis. So this is again another example. And then finally, we will go to millimeter wave lens antennas. So again, there are three things here. One is gain enhancement using all dielectric superstrate. Then you have high low epsilon anisotropic lens, and then you have thin planar lens for multi-beam MIMO. As I said, we have high gain antennas, then we have MIMO antennas, multi-beam antennas. So this will try to put everything together. So this is an all dielectric superstrate. So the superstrate is the arrangement is shown here. So this is all dielectric, and using again Maxwell-Garnett theory, your epsilon effective is about 1.41. Now the dielectrics here are modified as this. So you create these gaps here. So in one of our papers, a detailed theory of this is also given. You create these gaps here and then stack them as shown here. So what you see is this is black curve is epsilon effective of the substrate, whereas this red curve is epsilon effective of the 8 substrate with these air gaps. There are air gaps in between the substrates. Then we use that as a superstrate. So on the lower side you have patch antenna, and then this all dielectric and superstrate. So this is again a simple technique. This was verification. If we really require to have a metasurface to increase the gain. So what was seen here was there is significant gain improvement even with simply the dielectrics. So this is happening because the waves are passing through this, and the resultant or the effective permittivity of this is very close to that of air. So again, the phase equalization curves are not here, but it was also observed that you get phase equalization, and as a result, you get high gain along the forward direction. So this is a flat profile of the E fields. This results in planar field profile. So this is again here. This is argument of EY in degrees, and so this one is without superstrate, and the blue one is with superstrate. Blue one is with superstrate. So this is slightly better. So what the delta that we have is about 100 degrees, and here you have delta of 140 degrees. So this results in very high gain along the forward direction. Again, some part of the theory and mechanism of gain enhancement in this case. Next example that I would like to show is this patch antenna with a high-low epsilon lens. Okay. So in this case, the microstrip patch antenna is loaded with a user-defined medium with permittivity tensor, for example, 0.1, 10, and 1. So the permittivity is different along 3 different directions. So you have this experimental arrangement is shown here. This is microstrip patch antenna, and then you have high-low epsilon slab on top. So the S11 is shown here. This is the transverse magnetic field. This is transverse electric field. Now this is argument of E on the lower side and argument of H on the top side. So what we see here is for epsilon y equal to 10, and you get a flat curve. For epsilon y equal to 1, and you get a variation like this. So as you increase your epsilon y, what we see is your phase profile is constant across the y-axis. As you can see, this y-axis is this, x-axis is the horizontal axis. Likewise, for epsilon x equal to 5, 3, 1, and 0.1. Right? So again, you get in this region, it is taken as more or less flat, not much variation. So this is simulation, simulations are done. So in the simulation, you can define this high-low epsilon slab with the permittivity tensor 0.1, 10, and 1. So this was done in simulation. So this is gain versus media thickness. The thickness of the medium is varied, and we see that as we increase the thickness, the gain increases. And at lower thicknesses, you don't really get a single beam, you get dual beam type of characteristic. So this is the 3D pattern. This is without the metal lens. There's the microstrip patch antenna, and this is with the high-low epsilon lens. So you get considerably narrow beam with high gain. Now, how to realize this? Right? How do we realize this tensor, right, practically? But you won't get a material which has this type of epsilon characteristics. Right? So this was obtained by using metamaterial lens. So this is the unit cell. So it was repeated, and then along the plane, and then 7 such slabs were used. So and then after we combine this, we find out the permittivity and permeability. So what we see is Ex is this term. So this is for most region it is negative. This is epsilon y. So epsilon y is different than epsilon x, and this is epsilon y for 7 element array. So epsilon y, if we take 7 element array, it drastically reduces. So basically, you are using a metamaterial, stacked metamaterial in such a way that you realize the epsilon tensor that we started with. So instead of using a single slab like this, instead of using a single high-low epsilon slab, right, with this permittivity tensor, right, so the same permittivity tensor can be realized using metal surface lens. So that is what is shown here. So this is the overall dimensions. We have 14.86 cross 14.7 mm, the size of the superstrate, and this total distance is 7 millimeters, so not very high. So again, what we see here is we get considerable gain enhancement for 7 layers. For 3 layers, it is flat. For 2 layers, it is split beam. So for 7 layers, you get considerable gain enhancement. And what was also seen is if you increase the layers, number of layers beyond 7, there is not much increase. There is not much significant increase in the gain. Therefore, it was limited to 7 layers only. One can see in this comparison. So this is a high-low epsilon. So this is a hypothetical slab with the given tensor, and this is the same permittivity tensor realized using metasurfaces, stacked metasurfaces. So it was practically done. So good matching at the given frequency, 28 gigahertz, because it is the antenna is a microstrip antenna, and the bandwidth is not very high. In the earlier cases, it was dipole antenna, so the bandwidth was slightly better there. Printed dipole antennas, the bandwidth is slightly better. This is the realized gain. This is with microstrip patch antenna only, and this is simulated and measured microstrip with metasurface lens. So what you see is a peak gain of 13.8 dBi is achieved with this lens, and resulting in aperture efficiency of 99.5%. So this is very, very high aperture efficiency that has been obtained. These are experimental results. What we see here is this was published again in IEEE transactions on antenna propagation. So what we see is our main aim or the main selling point was this aperture efficiency, very high aperture efficiency, 99.8 and 95.4. So the gain, the peak gain is 13.6 with this type of aperture efficiency. So in other results, if we see, you don't get the peak gains are higher, but the aperture efficiencies are lower. Of course, the price that we pay is number of layers. The number of layers that we have is 7 layers. Then this is a thin planar metasurface lens. So this, I think, a lot of you are also working on this concept. So you have a lens, and then there is an antenna array below here. So the lens is made out of this particular unit cell. Now the shape of this unit cell is not entirely random. There was a lot of study done on this, and then this was the final structure. And so there were circular discs, circular annular rings, and then they were cut and bent. So there's a lot of background study that was done before this particular unit cell was obtained. And what is important here is the unit cell performance. So what we see here is the unit cell gives you good S21 across the.
Excuse me, sir. So again, the sound is not coming.
Sound is not coming.
Yeah, so now it's coming.
Achha, okay. So what we see here is the unit cell is a transmission type unit cell with very good pass band, 28 gigahertz band. The unit cell is polarization insensitive and response to transverse electric or transverse magnetic same with no change in response for angle of incidence. So it is polarization insensitive as well as insensitive to angle of incidence. It was realized. So this is the array of that unit cell. It was fabricated. And here you see there are three element array, and then you have 13 cross 13 unit cells of the cell. So again, the S parameters measured and simulated. Sorry, S parameters measured for both S11 and S22 are matching. This is S21, S33, S22, and S11. So again, they are more or less in the band. So we have 28 gigahertz band here. The gain improvement. So what we're seeing here is for three different antennas. So this is the first antenna P1. So what we see is the main beam is along 15 degrees. So for P2, the main beam is along 0 degrees. And P3, the main beam is along minus 15 degrees. So this is, so you have three antennas and 7-layer and a metasurface layer. You are getting three different beams with very high gain. Since this is normalized, so you don't see that the gain number again, it is only 0 dB. This is normalized gain. These are measured core and cross polarization patterns at 29, 31, and 30 gigahertz. This is the gain. So measured gain is shown with this solid blue curve, whereas simulated gain is shown with dotted blue curve. Although the peak gain is about 19 dBi, which is at 28.5 gigahertz, the aperture efficiency is very low. The aperture efficiency in this case is very low, only 26.4%. In the previous cases where we were using high-low epsilon medium, in this case, we are using high-low epsilon medium. It was also similar thing. There was a unit cell which was repeated along x and y axis, and then there were seven layers stacked together. In this case, the aperture efficiency was very high. However, for this case, only single layer and antenna array below, the aperture efficiency is one of the drawbacks of the work here, this particular structure. So that is all I had. So before I close, I'll just quickly give a recap of the entire presentation. That is what I typically do. So we started with some introduction to 28 gigahertz band and literature survey opportunities in this band. So we have seen high gain antenna with wide scan radiation characteristics, where you get with multiple beams, and compact antennas. I did not emphasize the tables where the parameters were compared with the reported ones, but the antennas were compact antennas. Then dual band generation technique with wide dual band bandwidth and realization flexibility. A new technique for gain enhancement using high-low epsilon medium, and then and as well as single epsilon highly anisotropic medium that was created out of periodic structure, and then finally thin planar metasurface lens with antenna array for multi-beam MIMO applications. So these were the things that I'll be happy to take. I think I've completed before time, much before time. So, but I'll be happy to take questions so that we have sufficient time for discussions. Are there any questions?
Yes, sir. Some questions are there.
Yeah.
Yeah, the question is, what is the difference between chiral metamaterial and DNG metamaterial?
Chiral metamaterials are completely different. DNG is double negative type of materials, but the characteristics may not vary along various axes in this case. Whereas in chiral case, in most cases, the characteristics would vary along x-axis, y-axis, and also z-axis.
And the second question is, when metamaterial acts as absorber and radiator?
Well, when metamaterial acts as absorber, so to basically if I take a metasurface, so if I take a dielectric substrate and print a pattern of metasurface on one side, right, and if there's nothing on the other side, right, other side is again dielectric, right, then in that case it may, it can work depending on your design. It can work either as a transmission type metasurface or reflection type metasurface, meaning it may transmit a particular band or it may reflect a particular band. Now, if you want to use the same thing as an absorber, right, all that you will need to do is you need to have a conducting backing. You need to have a conductor back on the other side, right? In which case the same unit cell may not work as an absorber, but it is necessary that you have a conductor on the other side so that there is no transmission. And in most cases, the unit cells that are designed for absorption are similar to the ones that are used for transmission or reflection type of metasurface. But the ground plane on the other side is necessary. The difference also is in the their resonances, the form of resonance that one has. So there are two types of structures, periodic structures. One is resonant periodic structures, and others are non-resonant periodic structures. So based on whether it is a resonant periodic structure or non-resonant periodic structure, one would get whether it is transmission type or reflection type, and then based on that you can create the absorption type of metasurface if you have a conductor backing on the other side.
Okay, so the next question is, what type of connector was used for millimeter wave?
So this is a end launch connector, and the one that we have used is an end launch connector from Southwest. There's a company called Southwest Connectors. So there's the connector, particular connector is called an end launch connector. So it is similar to your SMA connector, except that obviously the center pin will be very thin, and there are other arrangements as well. So it works up to 50 gigahertz. There are ones available up to 75 gigahertz as well.
And what will be the cost of this connector?
The cost of the connector when we purchased, I don't know the current price, but when we purchased it was about $210 per connector.
$210. Yeah.
That was quite some time back. It may have changed. The prices may have increased.
Right.
Okay, so here the another question associated with the previous question. Also,
Yeah.
effect of connector inductance was considered in design or not?
In design of what?
So in any of the design of antenna?
Not really. I'll just go to my slides. Are the slides still visible?
Yes, sir.
Yeah. So, for example, in this case, this is a simple dipole which was further modified. So, in this case, this entire connector was simulated. Therefore, any effect of any inductors or any fringe capacitances, they were already accounted for. They were not done separately, but this entire connector was simulated. It was not simulated only because the structures were not simulated without the connector. This connector was also simulated in the CST microwave. That's the reason in most cases the experimental and measured results are matching quite well. If this is not considered, then there are differences between experimental and measured results.
So another
So there
question
is,
was,
yeah.
is the anechoic chamber measurement setup is same at 28 gigahertz as for 3.5 gigahertz?
Repeat your question again. Is the
Anechoic chamber measurement setup is same at 28 gigahertz and 3.5 gigahertz.
Yeah, the anechoic chamber setup is used. So in an anechoic chamber, what you have is you have absorbers, right? And these absorbers are frequency dependent, right? And the frequency also decides the size of the absorbers. So something that works at let's say 3.5 gigahertz will work at 28 gigahertz as well, depending on the material it is made out of. So one can use the same anechoic chamber, except that the connectors, the cables that one uses should be suitable for 28 gigahertz. Otherwise, the anechoic chamber environment, you don't really have to change for 3.5 gigahertz measurement and a 28 gigahertz measurement. Most absorbers are wideband absorbers, so they'll most likely they'll cover the entire band. And the size of the chamber has to do more with the lower frequency than the higher frequency, because the size of the absorbers at lower frequency is much you know, larger than the one at higher frequency. So, and they are sufficiently wideband absorbers, so you don't really need to have a separate chamber for 28 gigahertz.
Okay, any other questions from the participant? I think so. You have cleared
So
all the
I have
questions.
one question. I have
Yeah.
one.
Yes,
Can
yes, please.
I ask one thing?
Please.
Just I was observing one slide where it has been shown that the measured uh, your results are better than the simulated results.
You
That is
remember
around
the slide number?
slide number 61 or 60 maybe. That was S11 when you were talking about the dual beam antenna.
61 is this.
Yeah, this one. And this the
Yeah.
measured results are better than the simulated one.
Not really.
For the one depth, yes.
Yeah, here, yes, yes,
For
here.
second one,
So,
for around
yeah,
25. Yeah, here it is better
yeah,
than.
yeah. So basically, the band has slightly shifted.
Okay.
If you see this dotted curve, which is measured curve,
Yeah,
right,
that is
and the solid one is simulated. So the band
yeah.
has shifted. That's the reason one sees. Of course, what you're seeing is so if I shift the band, if I shift the simulated results slightly,
Right.
right,
Right.
probably then you'll see that the simulated results are better than uh,
Ex-
at this frequency, but at the higher frequency, yes,
Yep.
the S11 for the measured case is better than the simulated one.
Right. Agreed.
Okay, thank you. So, thank you, participants, and I request Dr. Jayavardhan to propose vote of thanks.
Thank you, sir. Good evening to all. On behalf of IEEE Delhi section, APS chapter Jaipur, and IEEE Young Professional Affinity Group Bangalore section, I take this opportunity to propose vote of thanks to our eminent speaker, Professor Mahesh P. Abegaonkar sir, for sharing his finding and knowledge with us. This session was very interesting and full of knowledge. It gave deep insight into the topics and also revealed very interesting facts. I am pretty sure the precious knowledge that Professor Abegonkar gave us will definitely help us in our research. Once again, I would like to thank Dr. Mahesh for accepting our invitation and taking out time from their busy schedule. Thank you so much, sir. I also thank to all the participants for being passionate listener. I also thank to our chair, Professor M. Sharma sir, and our coordinators, Dr. Sanjeev Yadav sir and Devdeep Sharkar sir, for their support and help. Thank you, sir.
Okay, thank you so much.
Thank you. Thank you.
Thank you,
Professor.
sir. Thank you, sir.
Let us hope to see you again.
Yeah. We hope the situation gets better and we get opportunity to meet.
Yeah. So thank you, Sanjeev. Thank you, Jayavardhan.